Hello everyone, welcome to my YouTube channel. So today I'm going to discuss Tifr 2021 paper. Okay, this is part of MCQ section, and soon I will upload the true false section also. So the first problem is very simple one, and if you have already read Riemann integration, then you can easily solve it. So this is basically a nice in a nice form which you can find uh, just by using integral. So this is limit n goes to infinity Sn is basically given by 0 to 1 over 1 minus 4 minus x squared dx, and that is given by 5 by 6, and that you have already done in HS class 12, done in class 12, right? Also you can do it. So this one is simple. Move to the second one. This is the very nice problem. So number of bijective maps from G from n to n such that G of n by n square is less than infinity. Okay, so basically summation Gn by n square is convergent, right? So that will imply summation Gn by n square is Cauchy, right? So that means by Cauchy criteria, for any given epsilon greater than 0, there exists a natural number m such that summation small n equal to m to capital N Gn by n square, this sum will be less than epsilon, right? So okay, so summation, let's observe the sum actually. Summation n equal to capital M to 2m Gn by n square. So this one is actually G of m by m square plus G of 2m by 2m square, right? Which is greater than G of m plus G of 2m by 2m square, right? Why? Because Gm by m square is greater or equal to Gm by 2m square, because m square is less equal to 2m square. Okay, so then now since G is bijective, so I can assign, so G of capital M is a natural number, so that means G of capital M is greater or equal to 1. Now G of capital M plus 1 must be greater or equal to 2. Why? Say G of capital M is 1, then G of capital M plus 1 must be 2, right? Otherwise, if G of capital M is 2, then G of capital M plus 1 becomes 1. So basically I want to say that you have m plus 1 up to 2m. So there are m choice, right? Now you need to assign the value of G on M. Now G is bijective, right? That means if you want to assign the values, the value it can take, the smallest set must be starting from 1 to up to m. Okay, it can happen that G of m plus 2 is 1 and G of m is 3. That can happen, but I am saying that since here m choices are there and G is bijective, that means at least the value, the smallest value, possible value it can take, this set can take, is 1 up to m. That is obvious. It can be, say, starting from 2 to m plus 1, or it can be, say, 2, 5, 7, 1000 and so on. But I am talking about the minimal possibility. and the minimal possibility is this. Okay, this, so this statement is not properly correct, because it may happen that g of m plus 1 is 2 and g of m is say g of m plus 1 is 1 and g of m is 2. That can also happen, but as a set this is true. Okay, so that's why this sum will be greater equal to 1 to up to m by 2m square. Now this sum will be same as m into m plus 1 by 2 times 2m square, which is same as 1 by 8 m square m into m plus 1, which is same as m plus 1 by 8m. That means which is greater equal to 1 by 8. So now if I choose epsilon to be less than 8, less than 1 by 8, choose epsilon to be less than 1 by 8, then summation n equal to small n equal to capital M to 2m, this gn by n square, this is greater than epsilon. That's a contradiction. So that means this sum cannot be finite. So there is no bijective map such that this is finite. So hence answer is 0. Okay, so this is just application of Cauchy criteria of convergence. Okay, now this one is also a simple problem. Okay, so basically if you see, so starting from 2, right, so 1 minus 1 by k square is basically given by, so it is same as k square minus 1 by k square, which is same as k minus 1 by k times k plus 1 by k. Okay, now if you want to write limit n goes to infinity product k equal to 2 to n 1 minus 1 by k square, then you have this 1 by 2 times 3 by 2. Then if I put the value, okay, so k equal to 2, then you will get k equal to 3, you will have 2 by 3 times 4 by 3, then it is 3 by 4 times 5 by 4 and so on. And you can see that you can just cancel this. Okay, so then finally you have n plus 1 by n, right? So only thing after cancelling out, only thing you have, this is say limit n goes to infinity, limit n goes to infinity 1 by 2 times n plus 1 by n, which is half. So half is the correct answer. Okay, now the fourth one. So the fourth problem you can solve completely geometrically. Okay, so it is given that S is a set such that x belongs to R and x greater than 0, and 1 plus x squared times tan 2x equal to x. So you can write tan 2x by 1 plus x square, right? Now if you draw the graph, you will get answer. So take this function as say g and take this one as f. So you can see that limit x goes to infinity x by 1 plus x squared is 0, as well as limit x goes to negative infinity x by 1 plus x squared, that is also 0. So this is kind of the graph of g. Graph of g is kind of say something like this, then some this it tends to 0, and similarly this goes to 0. Okay, now if you want to draw tan 2x, so you can already, it is possible for you to draw tan x, right? And you can do the same thing for tan 2x, but you need to be careful because it is 2x. So here it is pi by 4, here it should be 3 pi by 4, here it should be 5 pi by 4, and so on. And the graph should look like this, because there will be a discontinuity at pi by 4, 3 pi by 4, 5 pi by 4. Okay, though so this is something like you have this and so on. So you can see that at each interval it just cuts one time. So that means at each interval from this to this it cuts exactly one time. So that means the solution set is countably infinite, and the solution is given by this, right? So if you see the solution set, this is given by, say, this one, this one, this one. So on each interval of, say, 2k plus 1 pi times pi by 4 to 2k plus 3 times pi by 4, in between you have these two function has common solution, right? So that's why this is countably infinite. Fine. Now go to the thing is that, so this is slightly non-trivial problem. I just want to give you an exercise and I want to give you a example. Okay, so if you don't know, try to think. Okay, see, so first of all I just want to give you an example which is non-zero function but that satisfies this condition. Okay, and the example is very popular example, which is, say, it is better to give you. So say if fx equal to e power minus 1 by x square for x not equal to 0 and 0 for x equal to 0. Show that f is infinitely many times differentiable, and this is a very nice counter example, and any derivative is 0. Okay, this satisfies this condition. Okay, now you get this function, right? Now your idea is to manipulate this kind of function. This kind of function is called some kind of bump function. Now you use this function to create some another function, okay, which is kind of same, and you will get different function which are linearly independent. Because see, if you take some polynomial, I am just telling completely different kind of thing. So in case of polynomial, you can see that if you have some function f, and if you do it square, or if you multiply it with some another function, then they are not linearly dependent. So if two functions are linearly dependent, that means they have just scalar multiple of each other. So that's why you can do some manipulation, and it is your work. Because see, I am giving you solution. That doesn't mean that I can just explain everything, because if I explain everything in detail, then it is not possible for you to think it properly. So TIFR questions are very hard. Even for me also, it is not always possible to solve all the problems, but in most of the time I am trying to give you hint. Okay, and this is one of the problem which you should think about it, because this is a nice one, and you can definitely find it out. Okay, and the intuition and the idea is completely depends on this function. Fine, so you should think about it. Now move to the next one. This problem is actually a simple problem, but you may think it difficult. So let's see. Okay, maybe I missed one problem, the problem number 6. Okay, let's see. Maybe I missed one problem number 6. I will make a separate video for this also. Okay, so the problem number 7, let a be the set of all real numbers lambda belongs to 0 1 such that this limit exists. Okay, So then see, the point is that lambda can be anything. If you just find out the limit, you will get this one. Why? Because limit p goes to 0 log lambda 2 power p plus 1 minus lambda 3 power p by p. So if p is equal to 0, then we will get log 1, which is 0, and in denominator it is also 0. So this is 0 by 0 form, right? This is 0 by 0 form. Then you can using rule, you will have, say, limit p goes to 0, 1 by lambda 2 power p times 1 minus lambda 3 power p times lambda 2 power p log 2 plus 1 minus lambda times 3 power p log 3, right? Just by doing derivative. Then what we'll have, you will get this is just a calculation, okay? So what I need to prove it, lambda times log 2, right? And 1 minus lambda times log 3. Okay, so now you can put p equal to 0. So then you have lambda log 2 plus 1 minus lambda log 3 by lambda plus 1 minus lambda, which gives you lambda log 2 plus 1 minus lambda log 3, which is the answer. So that means the limit doesn't depend on lambda, so you can choose lambda to be anything. Okay, so that means option D is correct, because lambda belongs to closed interval 0 1, so you can take lambda to be anything. So that's why it is closed interval 0 1. Fine. Okay, so now this is the question number 8. So let x is a subset of R and fn be a sequence of functions such that fn x goes to R, it converges uniformly to a function f, and this thing happens. Okay, and it is saying that if each fn has at most 7 discontinuities, then f must have 7 discontinuities. Okay, so we know, let Gn be a sequence of function continuous at some point x and converging uniformly to a function g, then g is continuous at x. This is the very important result and basic result. You can also prove it simply by just you can just easily prove it. This is a part of sequence of functions proof, right? If Gn is a sequence of function which is continuous at some point x, and it converges uniformly to a function g, then g is also continuous at x, right? Now suppose in this question, if fn has a convergent subsequence, fn has a subsequence fnk converging such that continuous at x, then since fn converges uniformly to f, that means if fnk converges uniformly to f, and we can consider fnk to be a sequence, and since fnk continuous at x, that will imply f is continuous at x. Okay. Okay, so let if possible the second one is false. Okay, let the statement 2 is false. So that means Dn has at most 7 elements, but D has more than 7. Okay, say so. Okay, now let f is discontinuous at some point A. Then we can say, this is very important, all but finitely many fn's are discontinuous at A. Why? Because if fn has some sequence, say fnk, such that each fnk is continuous at point A, then since fnk itself converges uniformly to f, then f is also continuous at point A. But I already assumed that f is discontinuous at some point A. That means except finitely many n, all fn must be discontinuous at A. Right? Okay. Now we are assuming that D has more than 7 elements, right? So let f is discontinuous at x1, x2 up to xk, where k is greater than 7. Fine. Now for x1, choose n1 such that fn's are discontinuous at x1 for all n greater or equal to n1. We can find it, right? Because we know that all but finitely many fn's are discontinuous at A. That means after some finite stage, all fn's are discontinuous at x1. So we can choose some n1 such that after that value, all fn's are discontinuous at x1. And we can do the same thing, right? Then fn's are discontinuous at xk for all n greater or equal to nk. Right? We can do the same. Now choose, say, m to be maximum of n1, n2 up to, say, nk. Right? Maximum of this. Then for all n greater or equal to m, fn's are discontinuous at x1, x2 up to xk. Right? For all n greater or equal to m, fn's are discontinuous at x1 up to xk. Now if k is greater than 7, that means for all n greater or equal to n, fn's are discontinuous at more than 7 elements, which contradicts the given condition, because in given condition it says that Dn has at most 7 elements. That means for every n, fn can be discontinuous at most at 7 elements, right? At most at 7 points, each fn can be discontinuous. But here we can see that for large n of n, which is greater or equal to m, fn's are discontinuous at x1, x2 up to xk. And so if we assume k to be greater than 7, then they also have discontinuity more than 7, which is a contradiction. Hence, this k must be less equal to 7. Okay, so that's why more than 7, this one is wrong. So this k must be less equal to 7. Okay, so this one is correct. Okay, this is just a simple checking. So if this is a theorem, f is continuous, then pH graph of f is path connected because image of f is path connected also, and you are taking the product. So f is continuous, so graph of f is path connected. This is theorem. Okay, and this will imply graph is connected, because connected implies path connected. Now there is a nice equation, I think you know, which is say fx equal to sine 1 by x, x not equal to 0, and 0, x equal to 0, right? So sine 1 by x doesn't attain 0, but it attains every value, sine 1 by x, right? From -1 to 1, right? And I define that at x equal to 0, it is 0. Right? And f is not continuous at x equal to 0, because f is oscillatory at that point, right? But it is connected. Why this is connected? Because f already attains all the values in between -1 to 1, okay, and except 0, at all point it is continuous, there is no point, and the only point there it is not continuous, it's x equal to 0. But since x equal to 0 is not attained there, I can just put as the value to be 0, as I just assign the value to be 0, and simply the graph becomes connected, but clearly f is not continuous. Okay, so that's why it is very important. Okay, so yeah, that's a very nice. Now come to the problem number 11. So what is the number of surjective map from this 10-point set to 2-point set? So if a map f is not surjective, what does it mean? That means image f is not equal to 2-point set. That means image f equal to singleton 1 or singleton 2. That means f is ultimately constant. This will imply f is constant. So how many total maps possible? So total number of maps is 2 to the power 10, which is 1024, right? Because we know that if cardinality of x is m and cardinality of y is n, then number of maps from m to n is n to the power m. That is simple one. And f is not surjective means it is constant. So only two maps possible for constant map. So number of surjective map is 1024 minus 2, 1022. Good one. Okay, move to the second one. So okay, so if V is a vector space over a field F, if V is finite dimensional, okay, if V is finite dimensional and T is a linear operator, okay, then consider the minimal polynomial. So consider the minimal polynomial of T, or characteristic polynomial of T if you think it is in its matrix representation, because V is finite dimensional, then clearly that map is 0, right? P of T is 0, right? So 1 implies 2, which is obvious. Now what about 2? 2 implies 1. So if possible, V is infinite dimensional, right? If possible, V is infinite dimensional. Okay, then you can always consider a linear map T from V to V, say T of x1, x2 up to this to be x2, x3 and so on. Left shift operator. Now it is your work that T doesn't satisfy any polynomial. Okay, though it is infinite dimensional vector space, you can think geometrically as a matrix, and if you write down the matrix representation of this, you will see that it doesn't satisfy any polynomial. Okay, that's why if V is infinite dimensional, you can always construct a linear transformation T, which is this left shift operator, such that there doesn't exist any non-zero polynomial this T satisfies. Okay, hence C is correct. Move to the question number 30. Okay, so T from Cx to Cx be a linear transformation defined on the complex vector space. Okay, now Cx is infinite dimensional, right? Cx is infinite dimensional. So in case of finite dimensional, we can write T in its matrix representation, and then we can find the characteristic polynomial and find the roots. We can say that are the eigenvalues. But here it is infinite dimensional, so we can't do this with that process, right? So we need to do it in a slightly different way. So what we can do, that if say it has an eigenvalue, okay, if it has an eigenvalue, okay, then so let lambda be an eigenvalue, okay, and let f lambda be eigenvector for lambda. So one thing is obvious, that degree of T of f lambda is same as degree of f lambda, right? And say degree of f lambda equal to d, right? Now you can consider a V f belongs to Cx such that degree of f is at most t. You can consider this V, and then clearly V is invariant subspace under T. Why? Because T sends any polynomial to its same degree polynomial. Now I am taking a subspace which contains all polynomials whose degree at most d. That means if I take any polynomial and if I see the image of that polynomial, then that image is also a polynomial of degree at most d, so that lies in here, right? So that means if I restrict T on this V, then it will give V to V the linear map. And since f lambda is a eigenvector, that means that is also an eigenvector of T of V. Now this is a finite dimensional, and this is T plus 1 dimensional. So that's why you can, this is D plus 1 dimensional, so you can write its matrix representation. Now if you write its matrix, so you can take the basis 1x up to x to the d, and then write the matrix representation. You will see that the eigenvalue is 1 only. Okay, that will imply exactly one eigenvalue is possible. Okay, so that means this has exactly one eigenvalue. Okay, move to the next one. So R power n denote the real vector space of sequence x0, x1 to this real numbers, define a linear transformation. This you can easily see. So what is the kernel? So if you take the kernel, so x0 equal to minus x1, x1 equal to minus x2, that will imply x0 equal to minus x1 equal to x2 equal to minus x3 equal to x4, and so on, right? So that means kernel of T has dimension 1. If you fix a value for x0, then it will determine all the values of xn for any n. That means kernel of T is one dimensional, right? Now image of T is infinite dimensional. Why? Because we know that kernel of T plus, dimension of kernel T, dimension of image T is equal to dimension of this, right? So dimension of image T, dimension of this is dimension of Rn. So this is infinite this is finite, so this has to be infinite. So image of T is infinite dimensional. That is fine. Now quotient vector space Rn mod T of Rn is infinite. That is also false, because the dimension of Rn mod T Rn is same as dimension of kernel T. So kernel T has dimension 1, so that's why this is correct. So second one is correct, option A is false. So this is on the simple one. Move to the question number 15. This is actually a very nice problem. Okay, so first observe that dimension of C over R is 2. Dimension of C over Q is infinite, which is uncountable. Okay, uncountable, right? So what you can do here, so first thing is that, so if X and Y are to F vector space, then X isomorphic to Y over F if and only if dimension of X equal to dimension of Y over F. This is a simple linear algebra fact. Now see, dimension of C over R is 2, dimension of C square over R is 4. So there is no R linear isomorphism. But dimension of C over Q is same as dimension of C square over Q, because both are uncountable and same dimension. So that's why they are isomorphic. So that's why there exists no R linear isomorphism from C2 to C, but Q linear isomorphism from C to C. And dimension of C2 over C is 2, dimension of C over C is 1. So that's why this is also wrong. This is also wrong, but this one is correct. Okay, so the only thing here is important, that is you need to understand that when two space are isomorphic, right? So if their dimension over the vector space are same, then they are isomorphic. Why? Because if you want to define an isomorphism, it is enough to define a bijection on the basis set. Then by using the linearity property, you will extend it on the whole space, and that will gives you a linear map. That means it is enough to give a bijection between the bases. So if both bases have same cardinality, then you can give a obvious bijection. By definition of set, you can define whatever bijection you want, and that will uniquely extend a linear isomorphism from that vector space to another. And similarly, if you don't have the same cardinality, that means you can never give an isomorphism, because an isomorphism means it first of all linear as well as it is 1 1 and on 2. Now if you want to define a map such that the cardinalities are different, then it cannot be both injective as well as surjective, right? So that's why it is not possible. So it's a simple problem but a conceptual problem. Okay, problem number 16, this one the easy problem. I don't want to explain it, you can just easily diagonalize this and then conclude the answer. Okay, this is simple one. Go to the next one. So the question number 17 is a very nice problem. So we know that if sometimes if you have given any n by n matrix and it is given that they are similar, then their characteristic polynomial and minimal polynomial obviously are same. That follows from the definition of this. But the converse did not to be true. But here it is asking about the converse, and the converse is true actually for 3 by 3 matrix and 2 by 2 matrix. Why this is true for 3 by 3 matrix? Simply, so two matrices are similar if and only if their JC form are similar. That means Jordan canonical form. Their Jordan canonical form are same. JC form is same, not similar, same. Fine. So it is given if 3 by 3 matrices are there, and if their characteristic polynomial and minimal polynomial are same, then they are similar. Why? Because that will impose the condition on the Jacobson, sorry, that will impose a condition on the Jordan canonical form, and their Jordan canonical form has to be same. Okay, under this condition. Why? Because say 3 distinct eigenvalue it has. 3 distinct eigenvalue. That means minimal polynomial must have distinct roots because it is 3 by 3 matrix. So that means they are both are diagonalizable. So they are similar. Okay, both are diagonalizable. They are similar because their characteristic polynomial are same and they are similar with the same diagonal matrix. Now say 2 distinct eigenvalues. Right? So that means characteristic polynomial must be x minus lambda 1 square times x minus lambda 2, right? For some lambda 1 and lambda 2. Lambda 1, lambda 2 can be complex number. That is, we are not interested in that. So that is true, right? So then x minus lambda 1 square, x minus lambda 1 square times x minus lambda 2 square. Sorry, x minus lambda 1 square times x minus lambda 2. Okay, so fine. Now, so what is the possibility of minimal polynomial? So minimal polynomial, if say x minus lambda 1 times x minus lambda 2, then they are diagonalizable, so both have similar. If minimal polynomial is x minus lambda 1 squared times x minus lambda 2, that means it has for lambda 1 one Jordan block of order 2 from the minimal polynomial and one Jordan block for order 1 for lambda 2. That means it is specific from the minimal polynomial itself. It is specific that what will be the Jordan block. So that means their minimal polynomial same. That means it is specified that their Jordan block has to be this. So that's why they are similar, because they have both same Jordan block. And if exactly one eigenvalue, then also the same thing happen. Depending on the minimal polynomial, you can see that there is exactly one possible Jordan block. If there is two or at least two different Jordan block, possibility of different Jordan block, then you can take that matrix such that their minimal polynomial characteristic polynomial is same, but since their Jordan blocks, Jordan canonical forms are all different, so that's why they are not similar. But in this case, for 3 by 3 matrix, if you study case by case, I have already done for 2 cases, only one case are left, that is exactly one eigenvalue. So the characteristic polynomial looks like x minus lambda power 3. So minimal polynomial must be x minus lambda or x minus lambda square or x minus lambda cube. And all 3 cases you can see that there is exactly one possibility of Jordan canonical form. That's why both has to be same Jordan canonical form, and that's why they are isomorphic. And that's why they are similar. So that's the thing. Now question number 18, this one is a nice problem. So it says that b is something like px belongs to qx such that p has at most degree 2 and pz is contained in z. So say px equal to say a0 plus a1x plus a2x square. So first of pz, it is contained in z. That means p0 equal to a0, that is contained in z. P of 1 is a0 plus a1 plus a2, that must contain in z. Now since a0 belongs to z, we can say that a1 plus a2 belongs to z. What of p of minus 1? P of minus 1 is same as a0 minus a1 plus a2 belongs to z. By the same thing, you can see that a1 plus a2 belongs to z, right? So a1 plus a2 belongs to z. Now from 1 and 2, what you can say that 2a2, if you sum it, 2a2 also belongs to z, right? That means a2 is integer or a2 equal to 2k plus 1 by 2 for some k belongs to z, right? Since 2a2 belongs to z, either a2 is integer or a2 equal to 2k plus 1. Now a1 plus a2 belongs to z, that is given. So if a2 is integer, so hence if a2 belongs to z, that will imply a1 also belongs to z. And if a2 equal to 2k plus 1 by 2, since a1 plus a2 belongs to z, that will imply a1 equal to also 2k prime plus 1 by 2, right, such that their sum belongs to z, right? Fine. So now you need to do the quotient by a, right? And a is collection of all polynomials here, such that their coefficients are from integers. So only thing you can see that if you take any polynomial, say f belongs to this p, right, you can write f equal to some f prime plus half times x plus x square plus half times x plus x square plus some g prime. F prime means it is, or f tilde, okay, or g tilde, okay, such that f tilde belongs to z, f tilde belongs to a, and g tilde belongs to a. This is only one possibility, and another one is, second one is, f directly belongs to a. So if a belongs to a, then you are fine. If a doesn't belong to a, then you can write f to be in this form. Why? Because in that case, if a2 a1 all are integers, that means f itself inside a, right? Because the coefficients are integer. But if the coefficients are not integer, that means you can write, say a0 belongs to z, right? So a0 a1x plus a2x square. So let me write it. So a0 plus a1x plus a2x square. So that means a0 plus 2k plus 1 by 2 times x plus 2k prime plus 1 by 2 times x square, which is same as a0 plus half times x plus x square plus k plus kx plus k prime x square. So a0 plus kx plus k prime x square, so a0 plus kx plus k prime x square, this plus half times x plus x square. So when I see it in the quotient, so in b mod a we have half times x plus x square as an element, and so this plus a and the a itself. So that's why the index is 2 only. Okay, if it is directly belong to a, then we are fine, if all the coefficients are from integers. Otherwise you can write it as a polynomial inside a plus half of x plus x square. That's why index is 2. Simple one, but fine. Go to the next one. So question number 19 says, if G be any finite group of 2021, then which of the following positive integers m gives a bijection? So observe, since G is finite, that means bijection if and only if injection, because this is finite group. Okay, so if you have an injective map, then it is automatically surjective, and this will give you a bijection, right? So injective map in the group, so group homomorphism, right? Okay, this is not a group homomorphism, this is just given that finite order, and so this is a finite order, and G goes to G power n is bijection. So it is just given that whether it is injective or not. Okay, so now what you can do, if you want to check this, it is enough to check GCD of this A, so GCD of this M 2021. So what is 2021? 2021 by this, if you factorize it, it is 43 times 47, right? Now, so if it is 43 times 47, that means G has an element of order 43. So if M is 43, and if so, say G has an element K of order 43, so that means under this map phi of K equal to K power 43 is identity, and phi of identity is also identity, so not injective. Similarly true for 47 also. But for 45, GCD of 45 times 2021 is 1. So that's why it is an injective map. Right? This is an injective map. So this gives you a bijection. Right? Because see, if G1 power m equal to G2 power m, okay, then it will imply that, so that means there's some common power, right? So the simple thing, if the GCD is 1, that means they cannot be same. Two powers cannot be same, right? So that's why 45 is the correct answer. Now 20 is the simple one. How many subgroups Z13 cross Z13 have? So the trivial subgroups as the identity and Z13 cross Z13 itself, right? Now all the non-trivial subgroups, all non-trivial proper subgroup has order 13. Now since G is not cyclic and it is 13 square, that means all non-trivial elements has order 13. So that means number of elements of order 13 equal to 169 minus 1, 168. Now any group of order 13, is cyclic because this is prime order, right? So this is cyclic, that means any group of order 13 contains 12 elements of order 13, right? So if you take H1 and H2 both a cyclic group, and if they have a common non-zero element, that means that non-zero element is the generator, because this is cyclic, right? Any non-zero element is a generator. Cyclic group of order 13, so any non-zero element is a generator. So that means they will generate the same subgroup. That means their intersection, if H1 equal to order 13 and H2 equal to order 13, then H1 intersection H2 must have order 1, because otherwise it has to be 13, because that is divides both. So H1 intersection H2 has order 1. So that means all the elements of order 13 are different, right? So that means number of subgroups of order 13 equal to 168 by 12, which is 14. So total 14 plus 2 is 16. So 16 is the correct answer. Okay, I hope you like this video. Please subscribe and share. I'll upload the second part soon.